So think about this for a second. Far out in the deep ocean, we're building these absolutely massive structures. Huge floating wind farms, gigantic aquaculture projects. They're a huge part of our future for energy and food. But how do you keep something that enormous from just being swept away by the raw power of the sea? Well, that's exactly what we're diving into today, the unseen science of anchoring our future.
I mean, really, let that question sink in. This is not some little thought experiment. It's one of the single biggest engineering challenges we face right now. How do you tether something as tall as a skyscraper so it can stand up against the full, unbelievable force of the ocean? The solution is, kind of funny enough, both simple in its idea and just mind-bogglingly complex to actually pull off.
All right, so to really get why this matters so much, we have to look at what we're trying to build out there in the first place. The open ocean really is the next frontier, and not just for exploring, but for our own survival.
You've got two huge things happening. On one side, you have these floating wind turbines, which are absolutely essential for grabbing the powerful, super consistent winds you only find way out at sea. These are a huge piece of the puzzle for our renewable energy goals. And on the other side, you've got these massive offshore aquaculture farms, designed to grow things like seaweed at a global scale to help feed a growing planet. Two totally different goals, but they share the exact same challenge.
And just so we're clear, this is not science fiction. This isn't something that's coming in 50 years. These projects are being designed, built, and put out in the ocean right now. The scale is just immense, and honestly, the stakes could not be any higher.
So what's the secret sauce? What is the key piece of technology that makes any of this possible? Well, it's something you'll probably never see, doing its job silently, deep below the waves. It really is the unsung hero of all offshore engineering.
It's called a mooring system. And when you hear that, don't just think of an anchor sitting on the seabed. It's the whole package, the anchor, yeah, but also these incredibly strong lines and all the connectors that attach to the platform. This entire system has to work together perfectly to fight the constant, crushing forces of wind, waves, and currents, just to keep that platform exactly where it needs to be, 24/7.
And of course, there isn't just one way to do it. It's not a one-size-fits-all deal. Engineers have this whole toolkit of designs, depending on, the water depth and what the platform is doing. Some use the sheer weight of these massive chains that just hang in a curve. Others use a mix of chain and super strong synthetic lines pulled semi-taut. And then you have tension leg platforms, or TLPs, which are just fascinating. They use these vertical tethers that are always under tension. Think of it like trying to hold a balloon underwater with tight strings. It keeps it perfectly still.
Now you might think they just, guess how strong to make these things. But no way. Designing these systems is an exact science, and it's governed by these super strict international standards. You can think of it like a global rulebook that every single engineer has to follow to make sure these structures are safe and reliable.
And right at the heart of that rulebook is this really important idea called a safety factor. It's actually pretty simple. It's a number that tells you how much stronger a mooring line has to be than the absolute worst-case scenario force it's ever expected to face. So a safety factor of, say, 1.67 means that line has to be able to hold 67% more force than the craziest storm imaginable.
But here's where it gets really interesting. Not all the rule books are the same. So one international standard might say you need a really high safety factor, 1.67, and we're assuming all your lines are working perfectly. But another standard might say, okay, you can have a lower factor, 1.35, but you have to design for the very real possibility that one of your lines has already snapped. So you get this fascinating push and pull between being extremely conservative versus being more practical and designing for real-world problems.
And this really gets to the core finding from the research, the idea that one single rigid rule for every single project everywhere in the world might actually be holding us back. The argument is that if we can tailor these safety factors to specific projects, we could unlock way more innovative and efficient designs.
Okay, so if the rules can be a little flexible, how on earth do engineers prove that a new design is actually going to work? How do they know for sure that it can survive the storm of the century? Right, because they can't just build a multi-billion-dollar platform, tow it out to sea, and just cross their fingers and hope for the best. So instead, they do the next best thing. They build a perfect digital twin of the entire system, and then they unleash a virtual hurricane on it. This validation process is incredibly thorough. I mean, first, they design the whole system. Then, using some seriously powerful software, they simulate every single force you can imagine. Wind, waves, currents, you name it. They analyze how the system responds, every jolt, every pull on the lines, And then, and this is the most important part, they check their computer model against data from real-world platforms to make absolutely sure their virtual storm behaves just like the real thing.
And this isn't just a theoretical process. It gets applied to a whole range of different designs. The research looks at case studies on specific wind turbines, the super complex physics of those tension leg platforms, and even the unique challenges of trying to moor a gigantic seaweed farm. It's basically a universal toolkit for proving these designs are tough enough.
So when you put all of this together, the massive projects, the complex mooring systems, these different rule books, a really clear picture starts to emerge about what this all means for the future of our oceans.
The main takeaway is this: a rigid, one-size-fits-all approach to safety, while it sounds good and it's well-intentioned, can actually pump the brakes on the exact kind of innovation we need to make these projects cheaper and better.
The real path forward seems to be in developing smarter, more flexible standards. By tailoring the rules to fit specific designs and specific ocean conditions, we can push the boundaries of what's possible and really make floating wind farms and ocean agriculture a widespread, sustainable part of all our futures.
And that leaves us with one final fascinating question to think about. The science of mooring has let us anchor our ambitions in the deep ocean. But as we build bigger and as we push out farther into even more extreme parts of the world, what hidden forces and unseen challenges are still waiting for us out there, just beneath the waves?